Hello friends. So in the last video for permutation and combinations, we started with the basics of what permutation mean or what combinations mean or what in general counting theory means. And then we also discussed a very important theorem which is called multiplication theorem. Uh, in this video, we are going to expand and deep dive into permutations and combinations, the formula that is widely used to calculate permutations and combinations, as well as how they relate together. Right. So we'll start with permutation. So we already discussed that what permutations is. So permutations is counting the ways to arrange or order something from a pool of different things, right? So let's say the problem says that we have to the how many ways are there to arrange our things from n things, or how many ways are there in which we can select our things and arrange them or order them from a pool of n things. So that is called a permutations problem. Now it won't be always stated very clearly that it is an arrangement or ordering or permutation problem. So by looking at the nature of problem, we have to determine whether it's a selection problem or a permutation problem. So we have already gone through one example in the last session where we clearly discussed how the question can be formed and how can we understand whether it is a permutation problem or selection problem. You can go through that video to understand that, right? So before starting, we are going to impose two constraints here for now. The first constraint is that all item in n is distinct. So there are no two similar item. Every item in the pool of n items are different, distinct item. And the second constraint is that a repetition is not allowed, which means that we can use one item at most once in a particular arrangement. So they can be used multiple times or more than once across different arrangements, but for a single arrangement, it has to be used only once. So one item cannot be repeated. So we'll also see what does that mean when we discuss a problem here, or when we try to generalize the formula for permutations. Okay, so we'll have to keep this in mind that we have put two constraints here, right? Later on, we'll remove these constraints and see how the problems can be solved. But for this video, this constraint is going to be hold true, right? Okay, so let's say the problem is that we have in total n distinct items, and we have to calculate the number of permutations of r items from this pool of n items without repetition, right? So how do we calculate it? So first of all, this is represented by npr. So when it is p, it is called permutation, and this n is the pool of distinct item, and this r is the size which has to be selected from that uh, pool and then arranged, right? So that is denoted by npr. Okay, so now we'll discuss uh, how can we calculate npr. Okay, so we will what we'll do, we will go through a box method that we all also touched upon in the last video. So what box method tells us, so what we'll do, we'll try to create r boxes. So let's say these are r boxes, right? So this is first box, second box, third box, fourth box, and this is rth box, right? So if I have to arrange R items from a pool of n items, how many ways I can arrange, how many possible uh, selections or possible ways I have to fill this first box. So I have n items to fill this box, right? When I have fixed this particular position, in how many ways can I fill this box? So I can fill this box in n minus 1. Why? Because the repetition is not allowed. So that's why we said that this is our constraint. If the repetition was allowed, this could also be filled in n ways, because one particular item could have been used multiple times in a particular arrangement. But since the repetition is not allowed, we are only left with n minus 1 choices here. Again, to fill this box, we have n minus 2 choice. To fill this box, we have n minus 3 choice. Similarly, if you generalize to fill the rth box, we have n minus r minus 1 choices, right? Because of the first, we had n minus 0. For second, we have n minus 1. For third, we have n minus 2. So similarly, for rth, we have n minus r minus 1 choices. So in totality, how many ways? How many ways we can fill up this or we can arrange our items? That will be multiplication of these things. So again, this is to do with the multiplication theorem, right? So this is n minus r minus 1. Now we know that this is nothing but n factorial by n minus r factorial, right? Because this can be written as uh, if we multiply it, and if we multiply enough numbers to make it a n factorial, we have to divide that by n minus r factorial to get this particular number. So this will come down to n factorial divided by n minus r factorial. So npr is n factorial upon n minus r factorial. So what if we have to arrange n items at a time? That means we are given n items, and we have to find the number of ways to arrange all of them. So taking n at a time. So we can directly put that into this formula. So that will be n factorial divided by n minus, and r is also n factorial, which is n factorial upon 0 factorial, which is nothing but n factorial, right? And without applying this formula, this can also be visualized with box model, right? So since we have to now we are drawing n boxes. The first can be filled in n ways, the second n minus 1, n minus 2, n minus 3, n minus 4, and the nth box will be n minus 1, which is 1. So this is nothing but n into n minus 1 into n minus 2 up to 1, which is n factorial, right? So if we have to arrange everything, then the number of ways are n factorial. And the simple example can be like, if we have letters a b c d e, and we are asked how many 5-letter words can be formed with this without repetition. So that will be 5 factorial, because we can fill this in 5 ways, we can fill this in 4 ways, 3 ways, in 2 ways, and in 1 ways. So that is 5 factorial. The important thing to note is that we have already discussed that it is without any repetition, right? Okay, so now we'll go with the formulation of combination and how it relates to permutation. So we already discussed in the last video that there is a correlation between the number of selections that can be made, or the number of ways of selecting our items from an items, and the number of ways of permutation for the number of permutation for R items from N items. That is the number of way in which R items can be selected and arranged. So what is that correlation? So we discussed that in order to count the number of ways in which we can arrange R items from a pool of N items, is that first we calculate the number of ways to select R items from N items, and then for each of those selections, how many ways are there to arrange those R items themselves, right? So let's say we denote NCR as the number of ways of selection. So this the NCR is represented to for combinations where N is the pool of item and R is the number of items that has to be selected. Again, R is the N is all distinct items, and the selection does not have any repetition, right? So we can say that NCR, which is the number of ways to select R items from a pool of N items, into R factorial, which is R factorial is once we make one selection of our item, then R factorial is the number of ways in which that selection can be arranged, right? And with the multiplication formula, so this is number of ways to select, and this is the number of ways to arrange individual selection. So this will give us the total number of ways of arrangements, right? Which is nothing but NPR. So NCR can be written as NPR multiplied by 1 upon R factorial, which is nothing but N factorial upon N minus R factorial into R factorial, right? So this is clear, right? Because we this we have already discussed in the previous video, or you can also go through that video and look at it again. But this is how we calculate the number of ways of selection. Also, there is a relation says that the number of ways of selecting R items from N items is equal to number of ways of selecting N minus R items from N items. Now, why this is the case? This is because let's say we have N items, right? And we have to count the number of ways in which we can select R items, right? So when we select R item from this pool, how many items are left? N minus R item, right? So if we select R items, we are left with N minus R items. So for every selection of R item, we are left with another set of N minus R item, right? So for ev uh, so for all of the ways in which we can select R items, we are also left with N minus R items on the other side, right? So that's why the number of ways in which we can select R item will also be the number of ways in which we can select N minus R items. So that's why we have this relation here, right? So let's discuss a very simple question. So this is the question which asks us to find the number of ways of permutations and combinations which can be made by taking 4 items at a time from 6 given distinct items without repetition. So these are again the two constraints that we have already set, right? So they are all distinct item and there is no repetition. So what is the number of ways of permutation? So permutation is NPR, right? So in this case we have to calculate 6p4, which is nothing but 6 factorial upon 6 minus 4 factorial, which is 6 factorial upon 2 factorial, which is 6 into 5 into 4 into 3, right? Because 2 into 1 will be cancelled out. So that will be 6 into 5 30, 30 into 4 120, 120 into 3 is 360, right? And what is the number of ways to select r items from n items. In this case, this is 6cr, which is 6 factorial by 6 minus 4 factorial into 4 factorial, right? Just 6 factorial by 4 factorial into 2 factorial, right? So 6 factorial by 4 factorial will be equal to 6 into 5 divided by 2 into 1, which is 15, right? So this is a very simple question in which we are just asked to calculate the number of permutation and combination, and then we are also given specifically that we have distinct item, and then we don't have to repeat the items in a particular arrangement or selection. So let's discuss another problem. In this problem, the question says that from 10 persons waiting in a queue, in how many ways can a selection of 6 persons be made so that, so we have two questions here. A specified person is always included and a specified person is always excluded. So first we try to understand the question. So there are 10 persons in a queue and we have to select 6 persons from them, and then we have uh, two constraints given in the question. The first one says that there is a specific person which has to be included in all the selection, and then the second the another question says that there is a specific person which has to be excluded from all of the selections, right? Now this is clearly a question of selections, not permutation, because there is no mention for any ordering or arrangement. So first we try to decompose the question. In this questions also, uh, uh, it is not specifically told that it is the repetition is allowed or not, or whether the items are distinct or not, because it is inherent in the question. There are 10 different, the 10 persons, and they cannot, they all has to be, they'll have to be a different person, right? And then repetition cannot be there because we have to select 6% from a set of 10 different person. So there won't be any repetition. We have to select 6%, right? So that's why it is not explicitly told. We can just infer it from the question, right? So, and this is also a question of selection that we already discussed. So in how many ways, so if I need to solve a, in how many ways I can select 6% so that one person is already always included. So if this constraint was not there, i would have I would have 10 c 6 ways, right, of selecting this particular selecting a team of 6. So these many ways would be there, but since there is a restriction, that means one person is always in the team, right? So in our solution set, one person is already always included. That means, so for every team, we only need to select 5 more% from a pool of 9%, because one is already fixed. So that means the total number of ways is 9c5, right? Which is nothing but 9 factorial by 5 minus 4 factorial into 4 factorial into 5 factorial, which is 9 factorial by 4 factorial into 5 factorial. So 9 factorial by 5 factorial is 9 into 8 into 7 into 6 by 4 into 3 into 2 into 1. So we can solve this easily. So 4 and 2 will go. This will be here, and this 3 and 3. So this will be 21 into 6, which is 126. So this is 126 ways, right? Now the second question is, a, a specified person is always excluded, which means that I can now reduce my pool from 10% to 9%, because I don't have to include that one person in any of the selection. So the total number of such the total number of ways of such selection will be 9c6, because now I don't have 10% to choose from, I only have 9%. So which will be 9 factorial upon 6 factorial into 3 factorial, right? Which is 9 into 8 into 7 by 3 into 2, which is 3, 3, 2, 4, 12 into 7, which is 84, right? So I hope this two are clear to you. If you are not following up or following along, please put a comment in the comment section so that I can take that in the next session. We'll go to the next section, next question now. So we'll go to the next question. The next question says that a cultural committee has to be formed of eight members from a pool of 9 Asians and 5 Africans. So in how many ways we can create that committee, which consists of, so there are two different questions with some constraints. So the first question says that the committee has to contain 3 Africans, and the second says that committee has at least 3 Africans. So one is says that it exactly has 3 Africans, and second says it at least has 3 Africans, right? So we'll first look at the first one, right? So in the first one it says that it has exactly 3 Africans. So how many ways do we have to select 3 Africans? So we have total 5 Africans. So we have total 5 three ways of selecting 3 Africans, right? Now once we select these 3 Africans, we since we have to create a committee of 8, we are left with 5 spot, and that has to be filled with the Asian people, because we have already exhausted the quota for Africans. So we have already selected 3 Africans. So we have to select 5 Asians from a pool of 9 Asians. Now why it is multiply? Because it is again the multiplication theorem, which says that for each of this selection I have to make this selection. So every three African that I choose, I need to select 5 other Asians to create that committee. So this will give me the total number of ways of selection, which is, so this is 5 factorial upon 3 factorial into 2 factorial, and this is 9 factorial upon 9 factorial upon 5 factorial to 4 factorial, right? So this is 5 factorial by 3 factorial is 5 into 4 divided by 2, so this is 10, right? 5 into 4, and then yeah, this is 10, and this is, so we have 9 into 8 into 7 into 6, and then we have 4 into 3 into 2 into 1. So I think we have already calculated that. So this is 8, this is 3, so this is 7, 321, so this is 126. So this is 126, so we have a total of 1260 ways, right? Now in the second question, it says that it should have at least 3 Africans, right? So how many cases do we have? It has that the committee have 1 African, it has 2 Africans, and it has 3 Africans. So when it has 1 African, what is the number of ways to form such a committee? So again, we have to select 1 African, and then we have to select 7 Asians, right? If it is 2 Africans, then we have 5c2 into 9c6. As 3 African, we have already seen this, 5c3 into 9c5. So these are the three options, three independent choices. So I decide to only have 1 African in my committee, so I have these many ways. So I have these many ways. So this is n1, let's say. This is n2 when I decide to have 2 African in my committee, and then I have this many ways, and this is n3. So the total number of ways will be n1 plus n2 plus n3, right? Right. So we have discussed quite few questions in this session. I don't want to create it any longer. So I'll cover other uh, questions and more formulas and more concepts in next few videos. If you have any doubt in any of the content of this video or the previous videos, just put them in the comment section below. Or if you want anything to be discussed or expanded further, comment that. Like this video, subscribe this video so that you get to know about all the videos that I put on daily basis.